It's 1973. IBM researchers are building System R, the first relational database. They're trying to solve a problem that sounds simple but turns out to be one of the hardest in computer science. How do you make multiple operations appear as a single atomic unit? Consider a bank transfer. You debit 00 from Alice's account and credit 00 to Bob's account. That's two writes. What happens if the system crashes between them? Alice has lost 00. Bob never received it. The money is gone not because of a bug in the business logic, but because the hardware was interrupted. Transactions were invented to solve exactly this problem. A transaction groups a set of reads and writes into one logical unit. Either all of them succeed together, commit, or all of them are rolled back, abort. The database guarantees that partial states never become permanent. The concept proved so powerful that for the next 50 years, nearly every database used transactions as a fundamental building block. When developers ask, "Do you support transactions?" what they're really asking is, "Can I write code that makes multiple operations that either all happen or none happen without having to reason about every possible failure?" The answer transactions provide is yes. You don't have to reason about partial failures. You don't have to write rollback logic. You don't have to handle the case where step 3 succeeded but step 4 failed. The database handles it. This simplicity is the entire value proposition of transactions. It's not about performance. Transactions often make things slower. It's about the programmer's mental model. Transactions let you pretend that your operations are atomic even when they're not, and the database enforces that pretense. The question the rest of this chapter explores: how much of this guarantee can a database actually provide, at what cost, and what do you give up when you weaken it? ACID is the most famous acronym in database engineering, and the most misunderstood. Let's go through each letter precisely, because the book makes clear that some of these properties are not what they first appear to be. Atomicity means that if a transaction contains multiple writes and something goes wrong midway, a fault, a violation of a constraint, an explicit abort, all writes from that transaction are discarded. The database is left as if the transaction never ran. Atomicity is not about concurrency. It's specifically about the all-or-nothing behavior on failure. Consistency is the imposter in the acronym. What it means in ACID is that certain invariants about the data must be true before and after every transaction. For example, in a double-entry bookkeeping system, credits must always equal debits. But here's the thing: the database cannot enforce arbitrary application invariants. That's the application's responsibility. The C was added to make the acronym spell ACID. As the book bluntly states, consistency is a property of the application, not the database. Isolation means concurrently running transactions don't interfere with each other. The ideal is serializability. Even if transactions run in parallel, the result is as if they ran sequentially, one after another. In practice, databases offer weaker isolation levels because true serializability is expensive. Durability means once a transaction is committed, the data will not be lost, not even if the machine crashes, the power fails, or the disk dies. Databases achieve this through write-ahead logs on disk and replication across multiple nodes. The book notes that perfect durability is impossible. All techniques are probabilistic approximations. But the guarantee is strong enough for practical purposes. Atomicity and isolation are the properties that actually matter for correctness. Durability is the reliability guarantee. Consistency is your problem. As distributed databases emerged in the early 2000s, Cassandra, DynamoDB, CouchDB, RIAC, some of them rejected the ACID model in favor of what they called BASE, basically available, soft state, eventually consistent. The claim was that ACID's strict guarantees were incompatible with high availability and horizontal scalability. The CAP theorem, published by Eric Brewer in 2000, was frequently cited as proof. If you have a network partition, you must choose between consistency and availability. ACID chooses consistency. BASE chooses availability. The book takes a sharp stance on this. ACID has a precisely defined technical meaning. BASE does not. Basically available and soft state have no formal definitions. They describe a general design philosophy: favor availability over consistency when there's a trade-off, but not a specific set of guarantees. When a vendor says their system is BASE, what they usually mean is, we've weakened some of ACID's guarantees to get better performance or availability. The specific weaknesses vary. One system might drop durability. Another might allow dirty reads. A third might not support atomicity for multi-row operations at all. The actual questions to ask any database system are concrete ones. What happens if a node fails during a write? Is the write committed, rolled back, or left in an unknown state? Can two concurrent transactions see each other's uncommitted data? If I write to two different keys in one operation, is that atomic? Acid versus base is a marketing distinction, not a technical one. The book's framing, the real question is always which specific guarantees a system provides, and under what failure modes they hold.